Good morning, everybody. I think we are gently starting with the second lecture, and as people creep in, we will see. Okay, so the plan today is it's just to keep on more or less the same line as yesterday, but perhaps being a little bit more detailed. And what I would like to cover, in fact, where is the laser pointer? I had one yesterday. Okay. Thank you, Maria. Thanks. I would like to discuss some, again, pretty general guiding principles of computational physics and try to focus on those principles who are particularly relevant for multiphysics and multiscale application. But just as a recap, maybe you already know all of these, maybe not, so it's always worth spending a few words on basic aspect of a computational physics application. So in the first place, all over in my lecture, I will make the assumption of locality and causality, which means that the amount of computational density is basically the number of operation, typically floating point operation, you need to update your degrees of freedom per time step. And since most laws of nature are local and causal, I seem to remember that Feynman in his book writes that at the end of the day, all good algorithms reflecting the physics should be local, and so meaning by this that the cost of updating a degrees of freedom should be independent of the system size, which is generally not the case, in fact, for most algorithms around. But in our lecture, I will be basically working within this assumption. Locality and causality go together, so causality means no simultaneous interaction, means, again, no action at distance, and that's perhaps something which, for instance, in gravitational simulation is not, they have sort of simultaneous interaction. So sometimes it is convenient to relax this condition, but again, during the application I will be showing, we'll be sticking to the causality principle. There is another very important property whenever you design any algorithm, which is stability, if you are, in fact, simulating a stable system. Sometimes you simulate unstable system, but the typical situation is that your system is stable, and the stability conservativeness, which means that your numerics should really make a strong effort to reflect the first and second principle, because this immediately reflects in the fact that your error, by error I mean the error introduced in the computational representation, will decay instead of growing. Otherwise you have an unstable algorithm. So this is a really very general guideline. If you have conservation principles in your physics, and if you have, as you do have normally, an evolutionary principle, which is entropy growth or anything related to that, you better make sure that your numerics reflect that. And consistency is another important property, which means that you should make sure that your algorithm, in the limit where the mesh size or the time step size goes to 0, you should recover the correct physics. And this looks almost like a truism, but there are several examples in which even if you go at the infinite resolution, you do not recover the continual limits. Just to give an example, there are some problems in turbulence modeling where by increasing the resolution, you make your results worse, just because the way you model turbulence might violate one of the principles, typical those ones. And this typically can hit back on you very, very hardly. Accuracy, of course, you know. I mean, it's, you would like to make sure that your algorithm not only goes to the correct limit, but it goes fast. So that you want to make the error decay fast. But we will not talk about accuracy very much. Efficiency, yes, we will talk about efficiency. So you should make your algorithm as lean as possible. So minimize the cost per unit update. And reversibility is something I would say that is very crucial for molecular dynamics whenever you integrate a Hamiltonian system. But for dissipative system, that's of course not an issue. So This is, of course, a full course in itself. This will be a course on computational physics. Could be an interesting thing to do, but that's not the point here. So I will basically concentrate on these two aspects, in fact. And a distinction I want to make clear, because I think this will stay with you whatever kind of computational physics application you will be involved with. The distinction between explicit and implicit method. Sorry?
Oh, yeah,
sorry, didn't see the question.
I have a question about your reversibility comment.
Yes.
I mean, the nature of nonlinear systems is necessarily that, or chaotic systems, that they're very sensitive to initial conditions. And so you're going to have explosive results from small numerical errors that are simply unavoidable. So if for like a large number of these systems you're talking about modeling, it doesn't seem like reversibility is even approachable.
No, it is approachable. What I meant by reversibility is, for instance, if you take the Hamiltonian equation of molecular dynamics and you use just any time stepper, you would have errors which prevent you from rolling back your trajectory. But there is a class, a specific class of time marcher, which is called symplectic algorithms, and Simone knows much better than I do, but which in principle allow you just to roll it, move it forward and roll it back and just get to the very same point. Now, I'm not sure you can do that bitwise, if this is your question. But what, and Simone can back me up, but what I meant by this, there are, if you, I mean, you can design time marching algorithms so that they have this property that they bring you back to the point you were coming from. And if you are not careful, most algorithms don't do that. I mean, so it was just a pointer in that direction. Now, if you have a chaotic system, that's a good point. Simone, what do you comment? If you have a chaotic system, you use Verlet, what happens?
You can always go back with these time invariant algorithms. There is, as you say, a large class of algorithms which are time invariant, meaning...
I suppose that would be an...
Well, microscopically, you can always design this algorithm which goes back to the initial point. But microscopically, so if you look at global properties, this is a different issue. There was an experiment from the 70s, from Belleman and others, where they show that, yes, go back to the initial point, but you always commit an error which is within the precision of your machine. So if you keep going forward and backward, in the end you would, change systematically your initial.
And this was for a symplectic.
This is also for a symplectic algorithm. That's because the
suppose
numerical representation is finite.
Suppose we give this assignment to the class that you all know the Henon-Hyles strange attractors, right? Do you? Well, suppose I give you a chaotic system. So the attractor is a strange object, a fractal. And what happens if I take the Henon-Hyles system, which is just three ordinary nonlinear equations, and I use some Verlet integrator?
Again, you can go back to the initial point. The initial point will be offset by, if you work in double precision, so 10 to minus 16.
But this will accumulate.
This will accumulate.
Okay.
So if you do it systematically.
So reversibility here, I should add.
That, can I ask something? So
Sure.
Because of that, the second error decay in the third point won't be true, right? You will exponentially deviate away from the true orbit in base space.
If their system is really chaotic, I think so. Yeah. I think so.
I guess if the algorithm is stable, then you have a random walk from the real solution. But if it's unstable, then the error will grow exponentially. So probably that's different.
I think there is one counterexample which are cellular automata, because you can recover fluid dynamics with a cellular automaton, and you can have perfect time reversibility.
No, okay, Jonas, you're perfectly right, but this is a very special case. That would be a different class. There are algorithms where you can run a dynamical system full Boolean, and at that point, round-off error is 0.
Wow. And you do recover fluid dynamics, so
Yeah.
you do recover fully chaotic systems.
The gentleman who was here yesterday, Kim Mulder, professor at MIT, was sitting on the back. In fact, he's one of the pioneers of this. And there is even a company. He founded a company where fluid dynamics was computed this way. It's nice to discuss, but this will be really long tangent. It's a very interesting piece of history of physics. There is a big quarrel on that. I'll tell you later on. It's an interesting story. But Steve Wolfram was there, yes. And there is a big dispute who was the originator. But anyway.
And a little comment which I
Yeah.
think it's, at this level, it can be.
This can be a full course, so we can stay on
okay.
this slide
Go ahead,
forever.
sorry.
No, please go ahead.
Ah, yeah, when you talk about atomic simulation, say molecular dynamics,
Yes.
it's quite different if you do, celestial mechanics or if you do condensed matter. The techniques may be the same, but it's quite different because if you do celestial mechanics, you want to be very accurate, very precise. So you want to work in infinite precision.
I don't know, he knows, I don't.
If you do molecular dynamics, since the system is in itself chaotic
Yes.
and mixing,
Yes.
then you can live with, low
Yeah,
accuracy.
yeah.
Even it's even better.
It's just a way of sampling phase space.
So it's really depends on
Yeah.
really what you want to do.
Okay, I mean, it will be really interesting to expand on each of these subjects. That will make an interesting course next time, and I'm really looking forward to, if you have ideas, we can certainly discuss it off the track. Now, let me go back to, again, to a very basic thing. I'm sure that some of you, at least, have been exposed to this, but I think it's worth discussing because that's a really general distinction on, which applies basically to any kind of computational application. So there are basically two methods. Suppose I take this as an example. I have a system which is described by some state function f, and this is some Liouville operator, which just means that this is the operator which is advancing the system in time, and it typically will have some dependence on the space derivatives, gradients, and so on. Now, the exact solution, formal exact solution of this system is, of course, written here. So time t is just the propagator x pel t as acting to the initial state f of 0. And this is easily written, but in practice, this can be a nightmare. A practical way how, to compute this system is just to do the simplest time march scheme, which is called Euler forward. So I think this doesn't need really any comment. So you move in time, t plus delta t minus t, which is basically this derivative, is equal L, the state vector evaluated at time t, times the time step. Now you recollect things, and you write hat is just a shorthand for t plus delta t, so the Euler integration scheme would look like that. So 1 plus L delta t ft. This is simple. This is very handy because L typically, once you put your equation on a lattice like this, L will be a matrix, a sparse matrix. Sparse means that in order to update, suppose that this is your unknown. So this is space and this is time. In order to know the value of my function at this time t plus delta t and this space location, if, for instance, L is just a space derivative or a diffusion operator, all I need to know are the values at time t of the three neighbors. So basically, I have a link, a space-time pattern, where I take information from here, from there, and from there, and I can construct the solution at the time t plus delta t. Now, this is called explicit because it really acknowledges the causality of the original equation in the sense that in order to compute the future, you only need the past, the immediate past, time t, or you can call this present state, and you go into the future just by taking into account the values in a small neighbor of the solution at time t. Now, this scheme is nice, and in fact, the interesting point is that normally this operation is very simple and very economic because typically this Liouville operator will be a local operator, a derivative or second-order derivative, so it only involves a small neighborhood. But the price you have to pay for this simplicity is that, in fact, if you look into this expression and suppose that L is, in fact, this is a stable system, which means that the eigenvalues of L are negative, okay? So the spectrum of the Liouville operator lies in the, the eigenvalues are negative, and let's assume that this is an Hermitian operator, so all the eigenvalues are real. Now, what you have to guarantee, if you look at the exact solution, take the norm of the solution, and the x pel t will be a number less than 1 if the spectrum lies in the negative side. So that's what we mean by stability. Okay, so the system, the initial condition will decay and eventually will decay to 0 if the system is stable. Of course, here I should have put also source term, which would eventually determine the asymptotic state of the system. But for stability purposes, I don't need the source term, so that's why I take this simpler form. Now, this property, the fact that the x pel t in the norm of x pel t has to be less than 1, has to be reflected by the numerics. And if you don't do that, which means, in fact, that the norm of 1 plus L delta t has to be less than 1. If you don't do that, the scheme is unstable, which means, I mean, I would need a picture, but I mean, I think you're really getting the point. If the delta t is such that this inequality is not fulfilled, your numerical scheme, instead of decaying, will blow up. And clearly, this is dependent, in fact, on the size of the eigenvalues. Call lambda the largest, a generic eigenvalue of the Liouville, you immediately see that delta t times lambda has to be of the order 1. So if your time step is much larger than this typical eigenvalue of a Liouville operator, the Euler scheme will fail miserably. In fact, will blow away completely. So that means that explicit schemes, so explicit means present to future, are lean, they are simple, but in fact they are subject to, typically they are subject to a stringent restriction of the size of the time step. So a typical way out of it, I mean historically and still today I think is very much used, is to do a little change, apparently very little change, but it's a big change in terms of computation. I think the most common scheme is the so-called Crank-Nicholson. And look here what happens. It looks like really a very minor thing. Instead, you compute the time derivative like this. So half hat minus f over delta t is the derivative. Now, instead of evaluating the right-hand side at time t, as I did here, you do something a little bit different. You take the average of f at time t plus f at time t plus 2 over 2. So past plus future over 2. So you are kind of mixing present and past. Why do you do that? Well, we will see. Because you now recollect, I mean, this is one-line algebra, recollect things this way. So half at, you want to build a propagator. So an operator which takes from time t to time t plus delta t. And in this case, the operator looks like that. This is just a symbolic notation. Because since L is a matrix, this is an inverse matrix. Right? I should have written 1 minus L delta t over 2 power minus 1. So this is an inverse matrix. And please appreciate, I mean, some of you might know, but it will not be difficult to show that even if L is a sparse matrix, even if L only implies, for instance, 3 neighbors, its inverse will be full matrix. And this you can understand because if you suppose now you expand this denominator as 1 plus L delta t minus L squared delta t squared, and you have all powers. Suppose L is a matrix like this, 3-diagonal. So it means that you only involve 3 neighbors. This is L. Now, if you take L squared by expanding the denominator here, you would have L squared. You can easily see that L squared will get 5. And when you do L cubed, you will keep adding diagonal diagonal in your matrix. So that means, in other words, that you have to solve a linear algebra problem, which is a totally different kind of complexity. Here you don't solve any matrix. You just do 3 operations, okay? Sparse matrix. Here you have a matrix problem to solve, which is a big burden. On the other end, the advantage is immediately seen is that this propagator, if you take the norm, and if L is real, can never be bigger than 1 if this property is fulfilled, okay? So that means that this algorithm is unconditionally stable. You can take very large, here I just doubled the step, but the implicit schemes can take your time step 10 times bigger, maybe 20 times bigger. Of course, you have to take care of the accuracy, but it's certainly a very effective way of increasing your time step. Price to pay is that your algorithm is now non-local because basically, and you can see that even in the space-time diagram. I mean, in an implicit method, the value of a mile known at time t plus delta t, because of this f hat, will depend not only on the values in the past, but it will depend also on the neighbor, simultaneous neighbor. So here I have broken causality just to buy large time steps. But the price I have to pay is that if this guy depends on his neighbors at the same time, the neighbors themselves will feel the influence of their own neighbors as time t. And so you see that there is a chain of information, and in order to get this point, I need to know the state of the system globally. This is a very simple exercise, but really contains the basic ingredients. So there is always in computational physics this trade-off, should I be explicit or implicit? For instance, commercial fluid dynamics pretty much relies on implicit method because it is perceived that people have invented good ways of solving matter problems, very efficient way, and so they are willing to pay the price of inverting a matrix. Actually, you never invert, you solve a matrix problem in order to march to time steps. I would say that for multiscale computing, this is my own opinion, it might be wrong, but I think we would rather like to stick to the explicit kind of algorithms because they are really closer to the physical nature of the problem.
This is true going from the first to the second line only if L is linear, right? You can do that operation. So
yes,
so specific class problems where L is linear.
No, that's right. But if L is not linear, what you typically do, you linearize. L would depend itself on F. And typically what you do, you do an iteration cycle where L is evaluated the previous. And normally this works pretty well. So I don't know of problems where the nonlinearity of L would change the conclusion I've drawn here. All I want to say is that in the sequel of my lecture, and I would say all over in the multiscale literature, I think explicit methods are by far dominating. And I think the reason is that they keep you closer to the physical nature of the problem you're dealing with. Okay? So no questions? Let me go on. Now, now if we stick to the, let's be now a little bit more detailed. The condition I gave in the previous slide is pretty general. Okay? It looks pretty abstract, although you get the point. Delta t should never be bigger than the much bigger than the fastest scale contained in your UV operator. Let's see what this means in a concrete example. I mean, you will be bored with this advection diffusion, but it's better to keep using the same equation for multi-purpose. Now, there is a link, of course, between all the requirements I've been listing in the first slide. And causality is related to stability, and a little bit as a joke, but only partly a joke. It's really related to relativity. The basic principle, which really applies all over explicit time marching scheme, is that if you have a physical problem, the physical speed involved in your physics, typically advection, but could be diffusion as well. So the speed of your physical, or the physical process you are trying to describe should never, ever exceed the numerical speed which is supported by the lattice you are running on. Okay? What do I mean by that? Take this equation, which really illustrates very well the purpose. Here you have two phenomena in action. You have advection and you have diffusion. We have seen that many times yesterday. If I do a simple Euler time marching and a simpler finite difference of this, please allow me not to write down the equation, but I think you will accept that if I have delta xf, I can do something like this, right? F plus minus delta over 2 delta, something like this, okay? So my numerical mesh is characterized by a given, think always in space-time. So I have a delta x in space and a delta t in time. If we use now the condition of stability I've shown you in the previous slide, you will end up with something like this for the convection. So u, physical u, times delta t over delta x should be less than 1. This in the mathematical literature is known as Courant number, or Courant-Friedrichs-Levy condition. And what this means is that the basic principle is this. Now, rewrite this in a different form, which is to say just bring delta x and delta t on the other side, and you can rewrite this as a physical speed less than delta x over delta t. But this is the numerical speed supported by your lattice. So if you violate this, it's a really principle numerical relativity. There is a maximum velocity in the lattice which cannot be exceeded. If you do exceed, it's very funny. If you do the exercise, you really find things like tachyons. You generate unstable particles which do not exist in the physical world. It's very, very fun. The same thing, of course, applies for diffusion. In diffusion, the dimensionless combination is diffusion times delta t over delta x squared, and again, this has to be less than 1. If you have more dimension, in 2 dimension will be 1 over 2, in 3 will be 1 over 3, so it becomes more and more demanding as you increase the dimensionality of your problem. So that means, again, do the exercise, bring delta x and delta t on the other side, that the diffusion should be less than the numerical diffusion supported by your lattice. Now, here, there are many lessons here. We could spend a lot of time on these slides, but just let me give you a general one, and I think easy to grasp one. When you do an explicit time integration of this system, you immediately see that diffusion is the time limiter rather than advection. Why? Because if you have to fulfill this condition, you see that d delta t must be less than delta x squared, right? Look at this. D delta t less than delta x squared. So this means that if I double my resolution in space and I want to keep up with that without losing stability, delta t has to become 4 times smaller. You see that, right? Which would not be true for advection. In advection, space and time are the same thing. They go together. So that is the reason why typically I'm familiar with, I was at least familiar with fluid dynamics. In fluid dynamics, we have both. And because of this restriction, which is very hard, it's a square dependence, so you cannot leave much of that. Because of this restriction, typically you would march this part of, at least of the equation, with implicit solvers. So generally, diffusion is one of the main reasons why people why people go to implicit schemes. So this is just as a general remark. I don't know, how many of you have been exposed to this kind of consideration? Because, well, Joe, I know, but some of you may not.
Let me make a comment.
Yes.
If D is a numerical diffusion, I don't think this applies.
Which one is the numerical diffusion?
If D is just put in for stability, if D is not real physical viscosity, then D will be proportional to delta x squared itself, and then this consideration.
D is a property of your equation.
Well, if it's a physical one, yes, but if you... Oh, okay.
This is a physical,
okay.
by definition. Sorry about that. So this is meter per second, this is meter squared per second, this is a given.
I think the point is that at least in aspect simulations, you never get to the point where you're actually resolving real diffusion. You just put in some artificial viscosity and keep a high diffusion so that you can actually evolve your system in time. So in most turbulent simulations, this is the case, or this is violated.
No, that's right, but you just mentioned it, that you are artificially correct.
Yeah.
What I'm talking about here is what we refer as direct simulation. You try to resolve all the scales that you have in your physical problem. Of course, if you cannot afford that, then you have to correct this precisely for the purpose you mentioned. But the message here is that there are 2 basic classes of method, and the motivation for going to implicit or explicit depend on the type of physics you have. And typically, diffusion is a strong driver towards implicit method. Yet, I will not present anything regarding implicit, and now let me instead try to, again, it's a very simple back of the envelope exercise, but let's try to get a feel for, you remember yesterday we were saying that multiscale computing is about minimizing the amount of computation you want to do. So let's try again, back of the envelope estimate of what we would gain by combining, in fact, a micro and macro solvers. In the following lecture, of course, we will see explicit examples of what micro means and macro means. But this is, again, something very, very general. So suppose we have an application where we have, and that's the way it really works. For a given, you have a given macroscopic solver which goes in time with a time step delta capital T. So this is a large time step. But every now and then, by doing this time marching with a large time step, you assume that you are making some mistakes, some error, okay? Because the real system, is so in going from year to year, you are somehow forgetting about some physical mechanism, which from time to time you want to bring back to your solution. So essentially, you have a chain where you have macro solvers. Every now and then you go down to the micro solver and back again. Okay, going from here and here, and these two arrows, of course, involve a number of mathematical and computational structures, but for the time being, we can ignore that. So the micro solver will have a small delta t step, and suppose now you do capital M large steps plus m small steps. And assume that you have a gap, I don't know how to call it, an amplification factor, which is the ratio of the macro time step solver versus the micro. This is really not comfortable in English. Macro and micro seem the same, but I hope you are with me. So that means that you are advancing in time. Suppose you compare with in fact, this is the amount of microscopic time, and the total time that you advance your system by combining the two is, in fact, 1 plus the gain, the ratio of the time steps over the elapsed microscopic time. That's really very trivial. I'm just taking this and collecting the microscopic part here. Same goes for size. So suppose that you have n, capital N, large time steps, and small n, small time steps. And this means that by combining the two, you can run a system, you can represent a system which is 1 time, which is the size of the macroscopic system, plus an amplification factor, which is the ratio of the 2 time steps. Okay?
When you write GT, it's not a product, it's an index, right?
Sorry, this is sloppy. This is G is just the gain in time step. That's why I call it G. It's just the ratio of the 2 time steps. Typically, let me give you some numbers. When you combine molecular dynamics and fluid dynamics, GT is 100. Now, of course, there is a trade-off on GT, because if the two methods are too far away from each other, it's very hard to combine them. I mean, this yellow arrow contains a lot of information transfer in space. So if the two methods are too separate, here there are interpolation and extrapolation, and they become very inaccurate. So this already belongs to the part of details which really depend on the application, specific application we are running. But in general, I would say that in order to obtain significant savings, if this ratio is 1, I mean, you're not gaining anything, right? Because you're running on the same time scale. So in principle, this gain factor should be huge, but not too huge, because otherwise, going from macro to micro will be exposed to very large mistakes, and you spoil the whole purpose. Again, as I tell you, typical number for fluid dynamics versus molecular dynamics is 100. In the case I was showing yesterday, we are running here the biopolymer. Since we are not using Navier-Stokes, we are using Boltzmann. Remember the hierarchy. We have Navier-Stokes, continuum mechanics, we have kinetic theory, Boltzmann, we have molecular dynamics, and we have atomistic dynamics. Typically, for historical reason, I would say that people couple molecular dynamics to fluids, and here the GT is order 100. What we do, for a reason which will become apparent next week, we couple Navier-Stokes, we couple, that's wrong. We use kinetic theory and molecular dynamics, and then our time gap, in fact, is smaller. Here we are using, this ratio for us is about 10, and I think even 5. So the gap depends on how far the method you use, how far they are in the hierarchy. But the point I want to make is another one. Now consider the cost of your application. Okay? Now let me take an extreme case. How much do I gain? Of course, this is not fair, but just to set up the perspective. How much do I gain by combining macro and micro with compared to the situation where I would run micro all along, which is foolish, but just to have a reference frame. So the cost of my multiscale application will be, and I introduce capital C, is the computational density, which means the number of macro operation of the macro solver per site, per step. Okay? I assume that both macro and micro live on a grid. That's not necessarily the case, but it's just to fix ideas. And small c is the same quantity, but for the microsolver. So the number of operations required by the microsolver to update 1 degree of freedom, one side, per step. So the cost, again, that's really trivial. The cost is capital C times capital L times capital M, because I have n times m is the volume in space. This is just one dimension, but in 3 would be n cubed, because I have n grid points per dimension, times the number of time slices. And each of these grid points and time step will cost me C, capital C, floating point operation. Same goes for the micro. And now I make this assumption, which is arbitrary, but nonetheless rather representative. The assumption is that I take as a reference case a case in which the number of grid points which I put is a one-to-one balance between micro and macro. So I have more or less the same degrees of freedom in the microscopic solver as in the macro, and I use the same number of time steps. So think of a parallel application where I would run the macro on a given computer and the other on the other computer. They would go just one-to-one, perfectly balanced, as a reference case. Now, the interesting point, and now the cost of this setup will be just like here. With reference to the cost of running just the microscopic solver, I will have a factor, a penalty factor at this point, 1 plus GC, where GC is the ratio capital C to small c. Now, the point is that the cost of updating a single macroscopic degrees of freedom is not that different from the cost of updating a microscopic degrees of freedom. Very often, this is less. The cost of updating 1 degree of freedom in fluid dynamics is by no means larger of the cost of updating the particle position in molecular dynamics. I would say the other way around. So while GT and GX are big numbers, big, 10, 100, GC is at worst 1. Typically is much less than 1. So that means that in principle, what I gain by replacing the multiscale chain with the full microscopic solution, can you read that? It's a little bit too on the top. But basically, I suppose that GT and GX are much bigger than 1, so I'm running a system which is GT times longer and GX times larger. So I'm gaining a factor GT times GX, which can be 1,000, 10,000, and the cost is basically the same. So just to, this is an extreme case, but it conveys the idea that just using small gaps can buy out large gains in computational efficiency.
There's something I didn't understand.
Yes, yes, please.
Is the assumption that the microscopic and macroscopic simulations are running at the same time? Or are you clustering the time axis? Are you running first micro and then macro?
I don't know. That's a good point. The way I thought about it is just serial, you see? Because that's the way, I mean, that really depends on...
I understand this formula if you are clustering the time axis, if you are having a serial point of view. If you're saying, well, let's abandon micro and do macro for some time, then you gain this factor.
Yeah, yeah, that's what I have in mind.
If you are having multiphysics, like in your DNA chain, which went through a hole.
What do you mean, Jonas? You mean something like this, that the micro and the macro would run on 2 different tracks?
Yes, when they both run at the same time, you don't have this speed up.
That's right.
You have to have more processor power.
Yes, yes. No, then we are going, I think that's a good point. What I had in mind with this extreme example
Yes, but then this is not
is the chain. And the heterogeneous multiscale method, which I have in mind as a framework for multiscale, works this way. The idea is that I would use the macro solver as much as I can because this is cost effective. But since I'm doing mistakes, please, I'm doing error, but not just numerical error. I'm doing errors because the macro representation is not exact. It's an approximation. From time to time, I want to go back to the more fundamental error. Remember what I told you yesterday. Always never forget the BBJKY hierarchy. And we want to think in terms of moving one level to another. So what I'm doing here, suppose I'm running a Navier-Stokes code, okay? In situation where sometimes I know that fluid dynamics may be not a good representation, for instance, for a microfluid. So every now and then, and here is the art, there is no general solution for that. Multiscale computing at the end of the day for real application is an art. You know that from time to time you want to go back to the fundamental level because you believe that you can heal your errors. So in that perspective, which is the perspective of a heterogeneous multiscale method, this is really a chain in time. But this is not the only possibility, so you're totally...
But in the application you showed us yesterday of this DNA chain which went through a hole,
That's perfectly
this
right.
would not be the case.
Absolutely. Very good. I'm very happy. So you're really with me. That's not the case. In that case, it's multi-level, because it's multiscale and multiphysics, because we have two systems running simultaneously. Yes, very good.
Maybe can I ask you? Was there any
Sure,
other
we
question?
can spend the entire lecture.
Yeah. No, I'm confused. If you have to do twice as many computations because you have to advance 2 levels at the same time, you have to use twice as much computing power at the same time, so you will spend twice as much time. How can you?
It's in
Okay.
absolute terms, but
No,
it
no,
depends.
sorry, I'm not sure I'm getting you. So let's make reference to this case. For the time being, focus on the case where time is sequential. So I'm not overlapping calculation in time. I'm just doing a chain, macro, micro, macro, micro. And of course, the blend of the two will be application dependent. If I do that, I think this little back of the envelope is correct, because I have 1 unit for the macro, say time, and by just doing one single time step in the macro, I will gain a factor GT.
This I understand.
Okay,
I
so
think
what is
that
your
I
problem?
will ask you
I
later.
guess the thing is, it's a small c in the equation down there. So you're comparing with your microscopic equation.
Yes, yes. I should have added here, for clarity, a chain where I have only green balls. That's the unfair comparison I'm making.
All the time, if you put this macroscopic description, you can save some time.
Well, yeah, that I understand. Yeah, yeah. Okay. Anyway,
It's extreme. I'm not trying to sell you this as this is an extreme case, but to fix ideas, please.
So I have a quick question about coupling the micro and the macro systems.
You mean the red, the yellow?
Yeah, the yellow arrows. So when you're discussing this, I in my mind, I'm kind of imagining, for instance, like you might be modeling like on a like say, for instance, in turbulence, you might in the micro state be modeling like the actual interactions of the molecules, for instance, and then in the
Some
macro.
people claim you have to do it. I don't believe so, but yes, that could be
And
an
then the macro sections, you would be doing like fluid dynamics,
Right.
where like each grid might be like 10 to the 10
Yes.
molecules, for example.
Yes.
That would be a huge difference. But
Yes.
so my question is, obviously in that case, you can't just interpolate and extrapolate like a picture in Photoshop. So you have to actually like store the information from the micro state as you're running the macro state and somehow get them to communicate with each other. And my question is how is that how is that done?
accomplished?
Do you like store that information while you're doing the macro steps
Okay.
and then have the macro step on
Right.
average affect
Okay.
the data?
That's you're getting to the point where, in fact, technical details, which really are extremely important, should be somehow discussed. Typically, there are many recipes. I mean, really, there is no universal. There is no theory of multiscale computing, right? Not the general method. But typically, I would say, as far as my experience goes, the way you transfer this information in space is essentially based on interpolation. The two keywords are interpolation, extrapolation, and sampling. And I will illustrate that with examples. But the specific way you do it, I mean, some people claim, and they think, some scheme, you have to have the micro and macro domains overlap a little bit, so you have an intermediate so-called handshaking region. And some people, some applications, the two domains just touch each other. So this really is highly application dependent. I'm pleased. Joy.
It's not a question really, but a request. Is could I request him to repeat his question once more? I just want to make sure that I heard it right.
I thought he was asking about the detail on how you move the information from two. Which question?
His question about marching.
oh, I think I understood the point. Well, there was the next question asked. My question was that if you, instead of doing it serially, you have marching with long time step, and then you stop marching with long time step and march with small time step, and then you come back. If you do this small time step marching at the same time, at not continuously, but from time to time, but in parallel, then I think that the answer would be the same as if you were to serialize them, because you would have to put more computational resource on the small time scale at the same time as you're marching on a large time step. But I
if you
think
compared if you did everything at the small time step.
if you did everything at the small time step,
Concurrent, what is called a concurrent approach.
yeah, if there was no stopping of the time small time, that I understood, like, the it's
Yeah, but-
then it would be different. But
I like to add
I
something.
think Jonas really got the point. I mean,
Sauro,
it's-
one thing that I like in the idea is what is called the multigrid methods. The multigrid is when you solve, say, the Poisson equation, right? You have a fine grid and you don't want to solve because you have lots of k vectors around. So you do a coarse graining and a fine graining, so some sort of ladder going up and down. That has nothing to do with time stepping and all that, but it tells you that you have different recipes, and that in that case you have
I will show some examples.
some operators which obey some rules, and you can get lots of nice properties out of how you define these.
Frankly
properties.
speaking, as Simone is pointing out, multigrid is, of course, is very important and still very much used method.
I can ask a question about that, if you don't mind. So when you mentioned the Poisson equation, that is a linear equation. I think that might be a big reason for why multi-grid methods work so well, and namely the coupling. I mean, at least physically, the coupling between the coarse grid and the fine grid is much. I mean, it should be, I guess, non-existent in theory, but it's much weaker. Is why you. I mean, this is why you can do this. So there's.
Yeah, but
there's,
even if it's non-linear, you can still play the same
But
trick, I think.
let me
That's-
try to recollect a little bit ideas. What multigrid is certainly, as I said, a possibility. But I think the type of the type of multiscale methods and multiphysics methods I have in mind are those where, in fact, you really change the representation along the BBGKY hierarchy. Just like I said, fluids versus molecules, and fields to particles, so to say. Multigrid is a way, very smart way of, in fact, I would regard multigrid as a way of working within the same macroscopic solvers at different resolutions. So that's only multiscale, but not multiphysics. Of course, you can always combine things, but in my view here, in my mind, here there is a notion that I'm changing level in the BBGKY hierarchy. Because that's the idea of correcting the errors I'm doing on the macroscopic solver is very much physically grounded. I correct errors because I go to a more fundamental level. That's the philosophy, okay? Of course, the philosophy has to be boiled down into practical tools, which I illustrate a little bit because this is really the part where the details dominate the scene, and you have the application, you have to work out your own details. I can anticipate the nightmare, not the nightmare, the real point is the boundary condition. When you communicate from year to year, you have to invent the boundary conditions, okay? But that will be the last part. So far, let's stay with the vanilla presentation, because one thing which I find kind of amazing, and I learned it recently, let's try to put this list computing principle in perspective in terms of how much do we gain in terms of years. And I find it amazing. Please double check on this because I might have got it wrong. But now let's ask a question, very practical questions. If I have a certain gain, if I'm gaining, say, factor 10 in space or in time, etc., how much do I gain? How much am I moving the frontier of knowledge I had? How much time am I saving? And we all know about Moore's law. Moore's law tells us that compute power doubles every year and a half, and I think Moore's law has been going for the last, 20 years or so. Now, let's try to measure, in fact, use Moore's law as a metric for estimating how many years are we gaining by doing multiscale. And again, it's really a very simplified picture, just to fix ideas. Suppose now by doing the chain I was showing in the previous slide, I gain a factor 10 in space or time. At this point, I don't care. So we know that, roughly speaking, if I gain a factor 10 in space and time, basically we gain a factor 10 to power 4, because I have 3 space dimensions and 1 time dimension. And it's rather amazing to notice that using Moore's metric, this is 20 years ahead. So, I mean, the gain can be huge. It's really almost silly what I'm writing, but I think it's one of the simple things which very far-reaching consequences. So we, the computational physicists, should be proud when we achieve it. If we have an algorithm which buys a factor 10, multiscale algorithm which buys a factor 10 in space and time, and the algorithm runs in a serious 3D environment, we are gaining 20 years of time to knowledge, and that's a big deal. And if you make 100, which I think is rather extreme, but still not undoable, that boils down to 40 years. So there is much scope. I mean, this, as simple as they are, to me, this is very recent to me. I heard this way of presenting things just a couple of months ago from Steve Orsa, who is one of the world leader in computational fluid dynamics, and his consideration were concerning, in fact, algorithms within fluid dynamics only. But this is a general statement. I mean, that applies to any computational scheme, and in particular for multiscale. I'm referring to gap because gap is what I called is the G factor I have been using the previous slide. So that means that the factor 10, which I think pretty affordable, I mean, it's 10 to 100, I would say, is a realistic size of the gap you can think of for multiscale. I mean, you are really moving frontiers a lot of, you are gaining decades in time. So that's it's a big deal. Now, local grid refinement, here I put this slide just because possibly I was anticipating some interest in local grid refinement, although I have not much to say, but local grid refinement clearly has the same potential. I mean, you refine 3 levels, and you're gaining 2 power 3, so it's already factor 8. And people do that. I mean, here I'm using an old slide when we were starting to work with TIM. This, I think, was a reaction. We wanted to have a catalytic reaction on a given surface, and of course it's silly to waste computers. We needed high resolution near where the chemistry takes place. And so that's certainly an effective way of doing it. But again, this is not exactly the spirit of multiscale I have in mind, because basically here we were solving the same equation on 2 different resolutions. So this picture doesn't really apply to what I have in mind with this arrow. Okay? But nevertheless, this is a perfectly decent, professional, and effective way of computing. Okay? And you can go further with that. This is, I drew from one of our applications in Rome long ago, and you can be more sophisticated and use irregular grids because this is a kind of a mess. But here our computing elements are basically tetrahedra. And with tetrahedra, you can have, in fact, much larger flexibility because you can fill space almost in an arbitrary way, and so you can save a lot of computing power. But of course, this code becomes more complicated. So the data structures for this are more complicated. This is there, I think, basically for fun. I think one is dreaming of a situation. That's in fact the dream. I mean, this is, I would say, needless for practical purpose because this is basically a cartoon. Suppose I have a calculation at the scale of, this is a real calculation. This is a calculation from this company is here in Boston using lattice Boltzmann for aerodynamic design. And the idea of the multiscale computation would be that you do fluid dynamics solver here, and here maybe near the wheel you need higher resolution because these are 3 movies, but they cannot move together. I don't know. I think my computer is suffering some lack of.
I'm sorry to interrupt. Is there a wall-layer model that they use?
Yeah. And in fact, that's near the boundaries. You have to refine your grid, and you have to do some. I mean, here from here is still the same equation. In principle, although for turbulence, I don't think this is necessary. Some people claim that the details of turbulence, or the way, for instance, vortexes are detached in the rear part of the car, would depend on the molecular details. I don't think so.
I'm just curious about the near-wall behavior. I think that's very important in estimating drag and things like that. So the near-wall physics is pretty important.
Yes, near-world physics, but here is just a qualitative representation. Typically, the near-world physics is treated by turbulence modeling because in a normal calculation, you don't have enough resolution. What they do, they put some grid refinement here. So what you may think of if...
They also have boundary layer theory.
They also have boundary layer theory, yes.
So they have grid refinement in addition to the boundary model, or
Yes,
they just have grid refinement?
No, they have both. So I don't know in fluid dynamics of any situation where you would need even a further level of resolution. But for instance, in crack propagation, you have this 3-level application. And I think this was planned as my last lecture. But this is, I think I put it there just to illustrate the idea that you change the representation. This is fluid dynamics, this is molecular dynamics. And in principle, you would like to run them concurrently. Yeah, I think it's a good time to take a break because then we are changing a little bit. I want to go back to the estimates we did yesterday and be more precise on that. So I think it's a good time to stop. Sarebbe bello girare una cosa così, la macchina con la... I think, Joy, I think Tim will not show up. I think he's sick. Yesterday he was feeling really very bad. Okay. Jonas. Est-ce que Bruce, parce que je voulais lui dire au revoir et puis il a disparu hier, est-ce qu'il va revenir la semaine prochaine?
Oui, je crois, il m'a dit qu'il pense revenir, mais il est très stressé ces jours, alors je ne suis pas sûr, mais je pense.
Autrement, parce que je n'ai plus son numéro de téléphone, j'ai oublié l'agenda en Italie.
Ah.
Je voulais lui passer un coup de fil au moins. Est-ce que tu as son numéro à la maison?
Non.
Bon, je lui file un email.
Il dit son email sur l'iPhone. Si tu envoies un email, il peut toujours ses contacts.
Ouais, d'accord.
You have had all those publications with Chen and other people on kinetic theory and turbulence modeling. Did you do some research on boundary layer theory, on turbulent boundary layers in the framework of kinetic theory?
Me?
Yes, or do you know somebody who
No. Maybe you don't. But it's very technical what they do. No, I don't think.
Because it's very interesting. I'm doing direct numerical simulations right now, and we have problems on which, with vortex wall interaction, turbulent vortex wall interaction, with lattice Boltzmann, we recover like much more precision than people who are doing the difference and finite.
This doesn't surprise me.
And I think there is something underlying in it, and I was trying to understand it better, but it's a very difficult topic.
It's very difficult. No, I'm not doing anything myself, but it would be interesting to know if you send me some draft or something, I can take a look at that.
Okay.
With the people in Rome.
Sorry?
With the people in Rome who know about turbulence.
Okay.
Thank you. Okay, so I think it's time to start. Oh, by the way, I should say that Tim asked me, Tim is falling sick, so that's why he's not here today. Now, let's move on. And I sense, of course, that you would like, of course, to get some more detail on how you do this thing in practice. And I'm not sure I can present much of this during the lectures because I'm sure you appreciate that as soon as you try to be specific on the way you do this coupling, you're really down deep into the details. It's very hard, I think, to present a general lecture on this. Also on the assumption that some people may be not really acquainted, very much acquainted with computing. But what I would really strongly encourage you to do is, if for your own application, try to think of a minimal exercise or a minimal assignment where you try to implement these ideas. And okay, I'm here for a short time, but we can interact even remotely. And try to think of some exercise, minimal exercise in your own field where you would apply this idea of moving across the BBGKY hierarchy. This is a general, I would say, assignment for this series of lectures. For me, it will be very hard to go into the details or how you do grid refinement, how you do but I will have some lectures like that, but they will still be rather generic. So whereas if you try to implement this philosophy for your own project, and then we can discuss the details later on during the next month or so. That I would be really very pleased to do, because it's a way for me to learn as well. So now, keeping up with the general guideline, let's try to, in the next lecture, I will try to give some details on how you do the, in fact, the scale and level transfer, and how you do the coarse graining, how you do. There are several words depending on the context. In physics, you will call coarse graining or averaging. In mathematics, you call projection. And an important piece, I think, of machinery, which is not present in multigrid, for instance, is sampling. Typically, how do you reconstruct the information when you are in the coarse level? So you have a macroscopic level, and typically I think of fields, continuum variables. And typically for the microscopic level, I think of particles. So multigrid is a way of transferring information within the box at different resolution. But what I mean by multiphysics and multiscale is the red jump, how you, in fact, reconstruct the microscopic state, which I think in terms of particle, based on this information. And as you all know, reconstruction cannot be an exact operation. You always lose information. When you project something, you lose information. And unless you have a lucky strike, there is no way you can exactly reconstruct that information. So there is always an uncertainty principle, literally, that if your coarse graining takes place on a scale h, in space of time, the commutator between projection and reconstruction, PR minus RP, will be order h, like Heisenberg, literally. Because, I mean, by the very nature of projection, you destroy information, and unless, I mean, it's not in the human capabilities to reconstruct exactly this information. Of course, you can try to minimize the error, and there are many methods, but sampling, I would say, again, in terms of keywords, is the keyword which is specific to multiscale and multiphysics, as I think of it in terms of jumping across the BBGKY hierarchy. And sampling is not found in multigrid or the traditional ways of transferring information across scales, but for the same equation. Okay. So, and I think a framework, I should have written the reference. I really encourage you to read the paper. It's in my suggested reading by Veinan and collaborators, because they try to formalize, in fact, this picture. And they have a nice paper, a long paper, where they present, in fact, the basics of the heterogeneous multiscale method, HAM. And here again, like always with human beings, there is a sort of dispute, because this heterogeneous multiscale method has also another name called equation-free approach. And it's really fair for me to give the names of both. They are both friends, and I don't want. So Veinan and collaborators, you find them under the rubric HMM. And they are systematizing, if you want, the idea of this multiscale and multiphysics. And there is more, I would say, physics-oriented. It's called equation-free approach, which is kind of catchy word, although it really doesn't really capture, in my opinion, doesn't really convey the idea. But but I think the person, Kevrekidis, which should be a knowledge. Do you have an eraser? Can you read here? Probably not. It's Kevrekidis. No, where is it? Okay. Did I put Kevrekidis? I'm not sure. Okay, fine. So just for the sake of, to be fair, I mean, these are two different names, but much of the material is in common. Anyway, it's a way of systematizing the idea that here the yellow box is where you do the microsolver, so you put it only in specific places, and eventually these places will also move around. So you can imagine, that's what they call underlapping. I don't know why, but it's a way of characterizing the idea. You do the microscopic solver only the specific places, and these places can change in time. So you can imagine that the machinery is not simple. But I want to go back to, again, to fundamentals and make a simple point, which I hope will stay with you no matter which kind of application we'll be dealing with. I want to pinpoint the issue of under versus over resolution. And that's, again, very simple, but one has to keep it in mind. So this picture, you know, we discussed yesterday at length, and you also know that, I think, at least implicitly, we introduced the notion of total degrees of freedom as the, in fact, the number of degrees of freedom that you have in the physical problem is the ratio of the macroscopic length versus the coherence length, which is really the smallest meaningful length for the macro solver, and same goes for the time. So here I have this G factor, which we have seen in the previous lecture. This is the G4 factor. And the amount of computational work which you do, of course, does not depend on the coherence length, but it depends on the affordable computer power you have. So if you fix your delta x and your delta t, the compute power will be the computational density, the C that you have seen before, times the number of grid points that you can put in your simulation, times the number of time slices. So it's interesting to notice that there is a sharp barrier here. It's again vanilla thing, but the consequences are somehow far-reaching. So the amount of work which you do per physical degrees of freedom, which is the relevant figure of merit you have to keep in mind, if you slash this and this, you get cost, which is a prefactor. Can change a lot from method to method, but it is a prefactor. Time these two ratios, which I call resolution in time and resolution in space. This is nothing but the ratio of the coherence time or coherence length versus the delta x that you can afford on your computer. Obviously, if this number is big, okay, it means that you can put many grid points to resolve your coherence length. So your calculation is very well resolved. If, on the other hand, this ratio is smaller than 1, it means that you have not enough power to resolve the coherence length, which is a typical situation in multiscale. The interesting thing is that, in general, you should not overdo your calculation. So you should make sure that you work in the vicinity of 1, because if you overcompute, if you put too much resolution, you are basically wasting your compute power, and you're wasting very badly, because this is power 4. In other words, remember what I showed you yesterday. And I keep forgetting the erase. If this is my coherence length, okay, and my delta x is this, then I have to find out a model because I cannot resolve it. So I want to resolve it, but I don't want to over-resolve it. If I do that, I'm basically wasting my computer power, because at this level, the coherence length is, continued theory doesn't make sense anymore. And you pay very hard for that, so be careful. That's why the coherence length is so important, because if you don't know it and you overcompute your problem, then you're wasting your compute power with the power 4. So you put a factor 4 here, it's already 4 to 4 makes what? 256. So you can easily waste your compute power if you don't have a good idea what your coherence length is. So that's just to stress what I said yesterday. I want to make a comment here because there was a question by one of you, and here, in fact, I have to make it more precise, but I will get to here later. Now, the other point that I insist so much on the coherence length because I think it's really a fundamental notion for multiscale. And I want to show you now how you derive it depending on the different physics. And I want to show you that, of course, it depends on the specific space-time physics you're dealing with. Now, as a general, let me take it again, a general perspective. If I have a coherence length L, there will be an associated time scale. And the time scale does not necessarily grow with the same power as space. So I will put an exponent beta here, which means that if I have a structure, take again a vortex of size L will have a lifetime t, and lifetime t will not necessarily proportional to its size. There will be an exponent, and I call this exponent beta. Now, the famous G, which we were mentioning yesterday, which is the coupling strength of your nonlinear field theory, actually, in all cases I know of, is basically a matter of competition. It's a competition between mechanism A and mechanism B. And when I say competition, what I mean is a ratio or typical time scales. A may be advection, reaction, diffusion, whatever, but G comes as a ratio. And this G will in general be a power of the capital G, which is nothing but the ratio of the space, the macroscopic dimension in space versus the coherence length. So from this, all I'm doing here is just taking A and B using beta, using this expression. So TA will be L coherence length of mechanism A versus L, power B. So you immediately see that the relation between the coupling strength and the gap in space is basically the difference between the beta exponents of mechanism A and mechanism B. Are you with me? It's really simple, but there are many symbols around, so if you are confused, please tell me. The point I want to make is that that beta really depends on the physics you are dealing with. I forget about this, I don't want to discuss that. So for beta equal 1, this is advection. In advection, if your basic mechanism is a convection, space and time are the same thing. In diffusion, space is much slower. You all know that in Brownian motion, in order to move twice as far, you have to wait 4 times. So that means that this exponent is 2. In other words, time goes with the length square, or length goes with the square root of time. There are many interesting phenomena, including turbulence, where in fact you are super advecting your information. So beta is less than 1. In other words, space moves faster than time, if I can use this kind of fancy language. And so this will, in fact, determine what I called yesterday the penetration index. So how powerful the continuum theory is and how deep you can go into the microscopic. Examples. Now, this is still general. You can reboil it into something which is very popular these days. It looks a little bit exotic, but I think it's relevant for multiscale, is the fractional relation between space and time. And I think you all know that we are used to the normal, in the macroscopic world, we are using to the notion of velocity as a ratio of space and time. And when you take the limit of a small delta t going to 0, the ratio is still well defined. So in an advection phenomenon, the ratio dl dt is well defined, and this we call velocity. But in general, there are many phenomena, and I would say the complex system I was mentioning yesterday in the early part of my lecture, I mentioned complex systems which are somehow rare events and fluctuation which persist. For these problems, typically the velocity is not well defined. And you have a generalized velocity, which here I associate with an index p, and this p is nothing but 1 over beta. And for instance, and this p can change. For instance, in diffusion, p will be 1.5 because space grows with the square root of time, and that's the typical situation of a random walk. So this Vp will be the diffusion constant. But in super advection, for instance, typically we think of the, in fact, P is a measure of how the degrees of freedom interacts with the environment. Okay? So typically in random walk, the environment is slowing particles down because collisions. So typically you think of interactions between particle and the environment as a slow down process. But for instance, in turbulence, the opposite is true because you can have a situation where you have a particle, you have a tracer, right? The tracer comes to a region where there is a vortex, and this vortex can speed up the particle, just like, so accelerating. And in this case, the exponent p is, in fact, greater than 1. So that means that the trajectory of the particle is over-persistent. So you are moving faster than advection. And in this case, in fact, the velocity, as you see, is not well defined, because if p, suppose that p is, in both cases, velocity is not well defined, because take the case of diffusion, if p is 1.5, clearly the ratio dl dt when you send dt to 0 is infinity, which means that this path is not differentiable. Okay? Whereas in super advection, the path is over smooth, because dl goes with a power larger than 1, so that means that the first derivative in principle is 0. So this is, just to to call the attention on the fact that we should not think in terms of velocity as the ratio of space and time, and we should think of a generalized velocity, because this power, in fact, is not necessarily 1. And this reflects very much into the coherence length. And let's take the case now, let's do the calculation in light of this notion of competition. The G of, let's take reaction diffusion, okay, chemical system with two species which are diffusing and reacting. The relevant number is essentially the diffusion time at the scale L, okay? So how much it takes, in fact, for the molecules to move a distance L versus the reaction time. This is called, the inverse of this is called Dunn-Köhler number, but that's incidental. We don't really care about that. What is interesting, though, is the fact that the diffusive time scales like power 2, whereas the reaction time is constant. So now remember that this alpha, the relation between the coupling strength and the gap is nothing but the difference of the two exponents. So in the case of diffusion, the coupling strength of the theory goes like the square of the space separation. Okay? Which means that the gap, which is the ratio of the macroscopic scale to the coherence length, goes like the square root of G, which is exactly what we were showing yesterday. So in other words, in a diffusion reaction process, the coherence length is just the geometric mean between the microscopic length and the macroscopic length. So the theory penetrates alpha way. That's what we did yesterday, and all I showed you yesterday, and all I did today is just to characterize this exponent in terms of the time. In fact, is the scale dependence of the time scale of the processes. You see, you have diffusion and reaction. Reaction is scale independent. We think of reaction as given by chemistry, but diffusion will depend on the scale you are considering. And it is this competition, which is scale dependent, which determines the degree of penetration of the continuum theory. Turbulence is more penetrating. And now I want to go a little bit more in detail and derive the exponent 3/4, which I was given for granted yesterday. Now, in turbulence, the relevant coupling strength, which runs with the scale, is the Reynolds number. The Reynolds number is velocity, remember, times length over viscosity. Now, multiply by L up and down, okay, and again, it's just one line calculation. The Reynolds number is nothing but the time scale of diffusion versus the time scale of advection. Advection is nothing but L over U, okay? Just do it, I mean, it's one line. So the Reynolds number, coupling strength of turbulence as a nonlinear classical field theory, okay, is the ratio of the time it takes to an eddy of size L to diffuse versus advect. That's an important notion, I think, pretty general, but just to make myself clear, if I have a vortex, if I have a vortex of size L, okay, advection is basically the time it takes for a molecule somehow to go around one time. And diffusion is the time it takes, in fact, for this vortex just to diffuse away and disappear and lose coherence. Okay? So when we do this ratio, and now, by definition, the coherence length is the crossover where diffusion and advection come to the same. Please do not forget that to me advection means, how would I say, advection dominates at the macroscopic scale. Remember what I told you yesterday. In the macroscopic bodies, inertia is crucial. Inertia dominates. So essentially, you have a picture where if this is a scale L, advection goes like that, and diffusion goes like that. When your vortex is very small, it has not enough energy to keep its coherence, and it will diffuse away. At that point, the continuum representation is gone. So this is, if you want, not a rigorous, but a precise definition of how you compute the coherence length. The coherence length is the length where the coupling strength is 1. I use that for turbulence. You can use that overall. You can take it as a definition. It's the crossover between the two competing mechanisms. And the interesting part is that the competition is scale dependent. If it's not scale dependent, everything is boring, right? Yeah, unless I'm mistaken here with the PowerPoint, L is a running scale. It's a running scale. So it's a generic length scale. Is any L? L runs over the strip. Capital L is the largest size of your problem. Okay?
Okay, so you apply your argument to just any LU which you find.
Yeah, I have a continuous spectrum of excitations. Sorry, the laser is gone.
Okay.
And I don't know why the laser is not. And L is just running over the strip. All I'm saying is that I'm trying to be more precise with respect to yesterday. And how do I define LC? LC is the scale at which the two competing mechanisms are in perfect balance. General definition. That applies. I'm using turbulence as an example to be specific, but it's generally true. I think it applies really to any field theory. By field theory, I mean a representation where your degrees of freedom are distributed. Okay? And at some point you are asking yourself, how deep can I go in space before I lose the continuous representation? I think this would apply to a quantum field as well, although I'm not an expert in this. But in general, I mean, that's where the competition is 1 to 1. Okay? Below that, for turbulence, that's what happening. Diffusion will be dominating. I will lose coherence, and then I have to go to the microscopic level. Okay? So that's a definition. That's also a definition, and I hope now I'm conveying the physical sense of it. And yet another definition. When people talk about Reynolds number for an application in an engineering sense, what they mean is the coupling strength at the largest possible scale. So when I tell you that the Reynolds number of a car is 10 to 7, is because I'm taking 100 kilometers per second. Sorry, I'm using the European gauge. In miles would be, what, 60 miles or something like that. I'm taking L as a meter or 2 meters, and I take in Ni as the molecular viscosity, because that's what it is. But this we discussed yesterday. I told you that this is a little bit unfair, not unfair, but actually I'm measuring, I'm taking the ratio of macroscopic quantities versus microscopic quantities, because this is dictated by the molecular world, and this is a macroscopic world. So in general, the coupling strength G, not running. When I tell you the Reynolds number is 10 to 7, I mean by this the value of G at the infrared limit. That's why it's big. Okay? Now, please believe me that if you combine these two simple lines will not be enough to determine the coherence length. And this is different with respect to reaction diffusion. Why is that so? Because, look here. I still didn't tell you anything about the scale change of U. U of L is the size of the vortex. Remember the picture I gave you yesterday, right? The spectrum of turbulence. I'm always referring to turbulence. Don't be bored. It's really, what I'm saying is really general in that respect. So I have let me put it in L. I have a spectrum of energy, and my car is here, and the big vortices are basically the same size of the car. Then remember what I told you. You go down because the vortices break down until they get so small that they lose coherence. But the question I need to answer to compute my coherence length is, how does the vortex velocity change down the line? And here, you don't have a theory. I promise you, nobody knows how to compute that rigorously. You would need a rigorous theory of turbulence to do that, even only statistical one. And you have to go back to Kolmogorov 1941. Kolmogorov used the simplest possible argument, which is still capturing, I would say, a good fraction of the physics of turbulence, although not all of it. And the Kolmogorov argument is very simple. But before I go into that, I really want you to appreciate that I need an extra piece of information, which is physics dependent, in order to know how the velocity, which is in fact my unknown field, when I say nonlinear field theory, I mean how the velocity field, how this is changing across scales. So Kolmogorov idea was very simple. He said, okay, I have an energy flux across the scale, and how about saying that this flux is scale independent? In other words, the amount of energy per unit length which I'm transferring from the big eddy to the intermediate eddy is just the same as the amount of flux, energy flux, which I transfer from the intermediate eddy to the small eddy. So the flux is what? Is the change of kinetic energy, I forget about mass here, so square of the velocity, over the time, typical time, lifetime of an eddy of size L. And since U is nothing but, L over T, this is nothing but U cube over L. So Kolmogorov postulates, and as I said, I mean, the spectra of real turbulence, to a certain extent, really follow this law. That means that the velocity scales like, kappa 41 is a constant, scales like the length power 1/3, which is a far cry from UL constant or UL power. Now, this has very important consequences. When I tell you that U of L scales like power 1/3, and now I ask you a very simple question. Is that field a gently behaved field, or is the wild horse? What would you tell me? I give you a field where the strength of the velocity is changing with the scale, so with the size of the, you can really literally think of a vortex, and U is basically this velocity, and L is the size of the vortex. Now my question is, fine, I make the vortex size twice as small. How does the velocity field scale with that scale change? And here is the answer. But can you figure out what that means in terms of the distribution of the field in space and time? That means that the gradients, can you differentiate such a field? You can't. If you take UL over L, this is L minus 2/3, and as you send L to 0, this is singular. Remember what I told you yesterday, complex system, large fluctuation, no central limit theory. And that's because you are generating wild horses, wild objects. So that means that, in fact, strictly speaking, in turbulence, you can generate fields where the gradients are infinite, and these are, in fact, sharp features which are very hard to capture by the simulation. That's why turbulence is so hard to simulate. Now, coming back to our little exercise of estimating what I called yesterday the penetration exponent, that means, since I'm comparing, the competition is between diffusion, which has a scale dependence L square, I have 2 here, and advection, super advection, in fact, which is this one, has an exponent beta 2/3, because it's 1 minus 1/3. If I'm moving too fast, you stop me. These are elementary calculations, but I don't want to lose you on this one, so please stop me if it's not clear. So remember, the alpha exponent is just beta of mechanism A over beta of mechanism B, and so this means that the coupling strength, the Reynolds number in the infrared limit, is the gap to power 4/3, and if I invert it, that means that given a certain Reynolds number, the gap I generate, which is in fact, and the gap immediately gives me the coherence line, is power 3/4. So just because of this singularity feature, turbulence is much more penetrating than reaction diffusion. So I hope that yesterday I gave you this 3/4 a little bit just out of the blue, and the reason is deeply rooted in the physics of turbulence. Now you see why this exponent really, behind this exponent there is a deep world. And I really insist, this is just an assumption. Nobody really, you cannot derive ab initio, there is no, and in fact there are corrections to these scaling laws, but they are minor. Okay? So this was a long digression, but yeah.
So this coherence length is really independent of the total length, just to make it.
No,
It's not. It depends on the
no,
total.
no, because unless I'm getting confused, I mean, what really I'm interested in is in, given the macroscopic length, what is the ratio, in fact, of the coherence length to the given macroscopic length. So what I can estimate is the gap between the two. So capital L will be given by the problem.
Just to understand your rules here, this rule that the Reynolds number at LC is 1.
That's a
That
definition.
fixes LC when I know this U of L.
Wait a moment. No. I mean, to fix LC, you have to have all of them. That's what I mean. That's a definition. You say coherence length is the length where I have the crossover between macro and micro. One requirement. This requirement is not enough. You have to use all of them.
Okay, and if I use that, I find a length scale LC, which depends on the viscosity, maybe the masses.
It will depend on the Reynolds number. You want to put the dependence in terms of dimensionless number.
On the Reynolds number, that depends on the total length L.
Yes.
That
When
I
people
don't
say
see.
Reynolds number, they mean this.
That I don't see.
Oh, it's the way it's given. If I tell you, oh, I have an airplane and my airplane is 10 to 8, it's because you're taking the cruising speed of the airplane, the total size of the airplane, and you're slashing with the viscosity of air.
Yeah, that's the total Reynolds number. I understand that, but the coherence length, isn't that something which only depends, according to this definition, the Reynolds number at LC is equal to 1. I can just
I see what you
evaluate that
mean.
using
Yeah,
your
yeah.
law for U of L.
Yes, you're right.
I guess the thing is your LM is fixed, so it depends on your L. Your LC will also change.
Yes. No, I see your point. Yes. You would say if I put LC here, I should get Reynolds equal 1.
Yes.
That's what I think that's true. But this doesn't clash with this conclusion.
No, I just wanted to see what
Yeah,
is
yeah, I
LC,
see what you mean.
just
Yeah,
to
yes,
see
yes.
the absolute number,
Unless-
because that
please.
is independent.
Please double check on that. That's a useful exercise. I can always be wrong. But I don't think so here. But please do that. I think you're right. I mean, if what I'm writing is correct, if you put LC here, you should get the coherence length. But this doesn't change the fact that if I want to know not just the numerical value, but how, in fact, I penetrate, then I need to know how my coherence length depends on the coupling parameter of my theory. And that would not be given to you if you just replace LC here. You agree with that? Okay? And
What do you mean with penetrating?
penetrating, I mean that I gave yesterday an equation which was somehow a little bit confusing, and now I will amend on that. But what I mean is the following. There is a prefactory, which I didn't comment yesterday, and that was a source of confusion, and we will correct that. Penetrating, I mean that I have an index. I can express the coherence length as an interpolate between the microscopic and the macro. And if this index is close to 0, I have a weakly interacting theory because the coherence length is basically the capital L. So it means that the continuum does not go very far into the microscope. There is not enough energy to support small-scale structures. In fact, reaction diffusion has penetration index 1.5. Okay? Turbulence is more penetrating. In fact, alpha, or A, I called the A, I guess, yesterday, is 3/4, which means that I can bring my energy to small scale closer to the microscopic cutoff. That means that the theory is a strongly interacting theory. Okay? Strongly interacting means that the energy can flow down the line and really keep the coherence almost to the microscopic scale. And that depends on how much energy I'm supplying from the exterior. And it also depends on the internal mechanism of energy transfer, which change from theory to theory. Turbulence is a given structure, but if you take another nonlinear interaction theory, this exponent will change. I don't know of any. It would be really very interesting to know if there are nonlinear field theories which can get really to 1. I don't know of any. So coming back to this discussion, yes, here there is a little amendment, but I would like to make sure that, because what I'm saying, all I've been saying is in a way trivial, but if you are confused, well, not completely trivial. This is certainly not trivial, but it's elementary, so to say. Nevertheless, I think the important point is that is to sort out, I mean, which gap can you fill given the macroscopic parameter which characterizes your application. And that's what people do in general. They give you Reynolds number, and then if I ask you, okay, I have a car, so where do I start to see dissipation in a car? Well, one way of computing is just you compute the Reynolds number of the car, which is about 10 to 7. You use this exponent, and you end up with some 10 or 100 microns, something like that. That tells you where you should stop with hydrodynamics. And the reason yesterday was that if you do multiscale computation, as I was showing in this morning, you would try to extend the red strip as much as you can, because supposedly in the red strip your computation is cheaper. So I gave you many reasons why you want to know the coherence length. If you over-resolve, as I showed you before, you have a factor over-resolution power 4. So you should not stretch, you should not try to extend the red line much beyond LC. You want to resolve the small structures, but not over-resolve them, because otherwise you're paying a lot of compute power. You're wasting compute power. Now, I want to amend what I said yesterday, because there were prefactors in this relation, and I was saying that, in fact, the coherence length in a turbulent flow starting at the meter scale can go down to 10 nanometers. I have to be more careful with this kind of statements, and because there are prefactors which matter. And again, I want to present a very simple exercise. Let's go through it very slowly. And we will see that it's very hard to push the coherence length below the macroscopic scale. In fact, it never happens. So this is the relation which we just found. The gap is proportional to G, which is the Reynolds number, 10 to the power 3/4. Now take the definition of Reynolds, so capital U, capital R over viscosity, power 4, and just rearrange that in terms of the coherence length. So you take the coherence length from here, you take 1L from there, and what you get is this relation. Okay? Now, I remember, I import a notion from the microscopic world, that in air, that would not be true in a dense liquid, but in air, the viscosity is basically the sound speed times the mean free path, which I take as a representative length of the microscopic world. Given this definition, I put it here, and please believe me that what I get is the relation I showed you yesterday. So coherence length as an intermediate between the macroscopic length, the micro, and the exponent is the one I gave you, but there is a prefactor. So the question is, can this prefactor be so small that the coherence length gets smaller than microscopic length? And you will see that's hardly the case. In fact, it never happens. In a typical application, to begin with, the macroscopic speed is generally smaller than the sound speed. Okay, there are supersonic flyers, but in general, this number is order 1, and if this number is order 1, clearly, LC is between capital L and small l. It can never get smaller than the microscopic length. Eventually, but I'm hearing out of my waters, if you really want to push it and say that you are a macroscopic object which is moving, say, 10 or 20 times faster than sound, I think this is artificial, but in principle, based on this equation, it's not impossible. Then eventually, the coherence length would become even smaller than the microscopic length. But I think this is a very artificial situation. So the message being that, in general, the coherence length is definitely within the two bounds. I mean, it's virtually impossible that the continuum theory can extend beyond the, can go below the microscopic length. Although, as I say, you can think of situation where if the macroscopic object is moving so fast that this prefactor becomes very small, in principle, this is, I did just the back of the envelope calculation. I think this would happen for Mach number of the order 20. I don't know whether a bullet, what is the speed of the bullet is what? I don't think it's more than 20 Mach. Anyway,
It's not an intrinsic property of the system, LC, but it also depends on the conditions you run the experiment. So it depends on you, the prefactor.
Yeah.
Then depending on that, you have to design a different experiment every time. So it's a bit uncomfortable, right?
No, it only means that, yes, I mean, what you would be given by the experiment here is, okay, the sound speed depends on the environment. I mean, if you are in air, you know what the sound speed is, and if you are in water, you know as well. And these are the experiment-dependent quantities. I mean, the size of your experiment and the velocity of your object.
With this size, one could live, but with you, it's a bit more thorny, no?
All I wanted to say that it is not fair to present the coherence length as just in terms of this exponent, because from the exponent you would infer that it is necessarily bound between the two. There is a prefactor, but normally this prefactor is such that all the more so L coherence is between the two. So when the coherence length gets very close to the microscopic length, you should be careful. Maybe you're missing some ingredient, and in my case it was this prefactor, which I didn't take into account. Okay? So I think we had enough of coherence length so far, but I hope at least you are now convinced that that's really a crucial quantity you have to consider. And if there are no questions, I would move to, how much time do we have, Simona? Ah, okay, so it's a good time to conclude. All I've been saying, remember the first slide this morning, the principle of causality. I'm considering a situation where, according to Feynman, in fact, the work I'm doing to solve a problem, the computational density, for some reason here I call it chi, is independent of the number of degrees of freedom, which means that the amount of work I do is just proportional to the volume in space and time of my application. But we have to nonetheless be aware that most numerical methods do not abide by this rule, and in fact the amount of work that you do to upgrade a single degrees of freedom is very often depends on the size of the problem. So we have been confining our attention to the simplest situation, which again I insist is somehow, I think multiscale methods tend to be effective in this region. But I mean, one has to be aware that in computational physics is a big world, and if you solve your fluid problem with a spectral method, the amount of, and you do it smartly using fast Fourier transform, then the cost per degree of freedom will have a very weak dependence on the size of your problem. Log is basically nothing, but in actual terms, but it's still not a constant. If you have a classical n-body simulation, long range, where every degrees of freedom has to talk to everybody else, then the density is proportional to the number of degrees of freedom. And this is an n-square complexity, which is very hard to live with. But there are worse situations in quantum chemistry when you have, or whenever you have to diagonalize a matrix. To diagonalize a single element of your matrix, you have to do a number of operations which goes with the square of the size of the matrix. And I think in quantum n-body, but I mean, I don't know exactly, but in principle, if you had to solve the Schrödinger equation for an n-body problem, I mean, the computational density would scale exponentially with the number of degrees of freedom. That is why we don't know, we cannot solve the Schrödinger equation for, say, 100 molecules, not even for 10. So just to keep your eye open on the fact that all I've been saying on the scaling exponent would suffer strong corrections if you use algorithms such that the computer density does depend on the size of your problem. And there are plenty of instances where this is the case. And I would like just to finish with some simple consideration. We have already discussed Moore's law, and we have seen that just by gaining a factor 10 in the gap between the space and time gap, we can advance 15 to 20 years along the Moore line. And I read recently a paper which I would like to bring to your attention. How long is the ultimate laptop? Have you ever seen something like that? It's by Seth Lloyd, who is here at MIT. I think the paper is kind of imaginative, but the question is an interesting one. So how far can you go before, in fact, you hit the limits of Moore's law? And imagine a situation where, this is just for fun, but I think it's interesting. The question is, if I have a laptop, and assume that a laptop is its weight in a kilogram, and it occupies 1 liter in volume, our present laptop are of the order of, can store about 1 gigabit, and they perform about, say, the clock is about 1 gigaflop, a billion operations per second. And it is interesting, the calculation that Lloyd does is to say, okay, let's think of a computer where we can put the degrees of freedom per atom, okay? And the conclusion that this ultimate laptop, still weighing 1 kilogram and still occupying 1 liter, taking into account the limitation of fundamental laws, say, so gravity, the speed of light is finite, and h bar is finite, it ends up with the following is that the ultimate laptop could contain 10 to the 31 bits and could perform 10 to the 50 operations. So if this ultimate laptop could be put in place, I think one could do even this kind of problems. But in order for this to be true, I think the Moore's law should go over for about another 250 years. So I think, just to say as for fun, that in fact one has to find methods to go about this complexity without waiting for the ultimate computer, because that's a long way to go. So summarizing, I think the basic idea is, and in the next lecture I will try to be I will give you some little examples on how you implement and concrete this idea, just to place the computer power only there and where it is needed. And by doing that, we have seen today that there are really huge strides in Moore's metrics. So we can gain really decades, literally decades, along the Moore line. But there are mathematical structures to require. We have not covered this, and this will be for next week. I will try to illustrate a little bit the kind of structures that you need to implement the program. And the success always depends on down-deep details, which for sure I will not be able to discuss. But if you have ideas, I shall be over-delighted to, on your own projects, over-delighted to discuss and try to see how they would be how this general philosophy would be implemented for your own problem. I think one beautiful point of all this multiscale story is that the general concepts are general. And so that means that try to think, for instance, in terms of this chain I was presenting this morning, doing as many time steps in the macro level, and every now and then go back to the micro and then up again. Try to think in these terms for your own application. And only then you will really have a solid grab on which kind of mathematical and computational tools you will require to solve your problem. And I can promise the ultimate question will be boundary conditions. The macro solver will set up the boundary condition for the micro, and that one you have almost to invent. If there are very few problems which have been solved this way so far, very few. It's just beginning. So you're mostly welcome to give it a try on your own problem. And of course, I mean, a question is, again, just to close on a philosophical note. I wonder whether nature doesn't seem to need this least computing principle. In the end of the day, the computational physics is just a struggle to make up with the outrageous gap of degrees of freedom between our computers and the real world. So we do need H multiscale mode, and nature doesn't do. But coming back to if you read into this kind of papers, which are fancy and give inspiration, but they all make the assumption that nature always processes the most microscopic level available. I wonder, and that's again for your imagination, whether one could think of a situation where nature would know itself that in order to evolve a vortex, you don't need to compute the molecular trajectory. Because if you can find instances like that, I think all these estimates will be drastically changed. So I wonder whether nature, I think biology is the only instance where nature seems to have a notion of building something functional. Try to think if there are any situations where one could recognize the fact that it is not true that only the nature just is processing the most elementary degrees of freedom, but instead recognizes that there are ways of handling collective degrees of freedom. Because if nature would work that way, these estimates would think completely wrong. But anyway, this is philosophy. The real thing is this: mathematical structures and down deep details. So next week we will be a little bit more solid on that. But if you can start thinking on this, that would be fun, because then we can do concrete exercises. Okay, thank you for your attention. If you want, if you feel like you have time, try to, I think I was preparing sort of a sign. If you want to, it's just the back of the envelope, but it could be a useful exercise. I think with the simple notion I gave you, you are certainly in a position to answer this question. You want to do it? Actually, I should have printed this out. Anyway, just do the first one if you want. I mean, what?
Put a link to it on the web page.
I can't hear you.
Can you put a link to that on the web page?
Yes, yes.
There's a web page for the course.
Okay, thanks for your attention, and see you on Monday at Jefferson, I guess. At Jefferson, I guess. I don't know, in fact, which.